Go on. When we first started the project, the goal, when we said we're going to shoot these unfiltered, short, really short duration images, just a few seconds long. It's a crazy goal, is to say, what we want to do is to see if there could be flare events or some sort of events that occur in there that may even be shorter than the 2 or 3 seconds that we have the shutter open. And if we had the shutter open for 3 seconds and something passed in front of a background star, there's 1,600 stars in there, I think I told you earlier that we can see. And if something passed in front of that background star for 3/10 of those 3 seconds, it's going to look 10% fainter. And so the idea is, can we make a histogram of the brightnesses that we measured on a given night for a given star and look for events like this that say there's something weird here where this star looked fainter in that image. Can we count those up and see if there's something going on there? And it's a fun project, it really is. But there's all kinds of things that go on. There's all kinds of cosmic rays that hit the chip. There's all kinds of geese that fly over, mayfly hatches that occur, things that happen that you have to go in and try to track and try to come up with some kind of statistical way of saying what looks astronomical and what looks terrestrial and start to peel that out. And then even if you do, you've got to convince the world that you've done a good job of that, and the world is very dubious. So, you know, it could be something passing in front of a background star. It could be a dense object that passes in front of it that made a very brief gravitational lensing event and made the star look brighter. So at least this could be a brightening event or a dimming event. This, we generally do, not always, but we generally do not profile photometry, but aperture photometry, just because it's quick. And then we can go back in and do other fitting photometry if we want to. But we can get through all of these stars in a night by drawing a circle around the star, adding up all the light that's inside that circle, and then having a background annulus for the sky background. And we had a satellite fly through the background sky annulus, and that's where that came from. So we subtracted out too much light in that one image, and you can go back and see these sort of things. I like to keep this slide in that talks about this because Amalia made that slide. And so Amalia worked on the project for one summer. A lot of sometimes students will work one summer, sometimes just a January term, sometimes a summer, a January term, the next summer, the next January term, the next summer, and the next summer. And try to encourage students to go out into the world and get other research experiences as well. But that's hard to do. You got a student who's really learning and really starting to become helpful. And analyzing data, you don't push too hard to get them out into the world. You go, oh, you want to come back next summer? Great. You can write code or help us do this sort of thing. Amalia worked on the project just one summer there. She's in a physics position at Hendrix College in Conway, Arkansas right now. Siri and Robin were really the first students who took this on when we decided we were going to switch over to do this, optical astronomy, and try to take all of these images. And Siri worked on the hardware that first summer when we were trying to learn how to shoot flat fields. I was an X-ray astronomer. I was not an optical astronomer. I was learning what had been done, what hadn't been done, and how we did this. And Siri helped with the equipment there. Robin did a lot of calculations of event rates of various size objects we might see there. Siri's an engineer at Boston Scientific in Minneapolis right now. Most of our students come from Minneapolis, St. Paul. That's the #1 place we would draw students. And so Siri's at Boston Scientific as an engineer. Robin is in the physics department at St. Mary's University in Winona, Minnesota. I came there from, this is a version of a draft, the first paper that I published with students after I got to Wilkerson College. And I came there from an X-ray astronomy community where I was really an instrument builder. I built high-pressure xenon gas scintillation chambers. 20 atmospheres of xenon gas in a tub. An X-ray would come in and hit that and make a flash of light in the vacuum ultraviolet, lay down in the ultraviolet, and we would see that. There were some papers out there that suggested that there might be infrared yield. And if we got more yield, we'd get better energy resolution. So we were looking to see if we could capture infrared emission along with the ultraviolet emission to give us more light to do this sort of thing, to build an X-ray detector, to fly on a balloon, to look at often like neutron stars with normal star companions would be X-ray pulsars. This is what we were trying to do. The problem was, the students loved it. The students actually did a good job with it, but what I learned was they were scared to touch the equipment. This was a very equipment-heavy thing. They wanted to write software and they wanted to play with data, but they were really scared to touch this. And probably if you've got 20 atmospheres of gas in a vessel, they should be a little bit scared to touch it. There's a lot of stuff there to worry about and to work with. And what I found was that in my first years, this is my 16th year at Wilkerson College, and in my first years there, I was spending all of my time tracking down leaks in vacuum systems and fixing pumps and teaching. So I'm teaching 7 courses a year at that time. And so I had a little bit of time each week I could go into the lab and work. And what I found is almost 100% of that time was trying to figure out where a leak was in the vacuum system or changing diaphragms in a diaphragm pump or something like that. So we moved away from this. So what we saw, just, was that actually the infrared yield was very high relative to the vacuum ultraviolet yield. Once you got down to 0.3 of an atmosphere, but where we were working up at 20 atmosphere. And it was not high at all up there. And if you have 0.3 of an atmosphere gas, it doesn't stop it. Your electrons flying. It just didn't prove to be. It was interesting, but not useful for what we were trying to do. So we moved on and started this other project on the roof of the science center where students could be involved all the way, every step of the way through. They're taking the data, understanding what a good night was, understanding how you had to calibrate data, and the kinds of things you could do. So, in flare stars is one of the things that we've been looking for to say, we have all of these images, short time scales, all of these stars. Is there any evidence of weird large flares occurring in stars, kind of optical transients that are uncommon, that we might stumble across because we have so much data? This is Kirsten and Clara have worked on this these projects. Clara's a senior right now. She's going to be a high school teacher. Kirsten is working as an engineer at Boeing right now. These are the kinds of things that we look for. Sort of a classic flare shape, where you have one of these faint red stars and has a hard leading edge and an exponential decay on there. And Kirsten did a lot of work simulating how good we would be at detecting those things. What shapes would we be able to detect with what efficiency, and what shapes would we not be able to detect? And Clara's going through our data right now and trying to put at least upper limits on the number of these flare type events that we would see. We also see not classic flare shapes where you might see something that's a star. This is minutes across there in this scale, and this is days across here in this scale, where it looked like something got bright for 2 or 3 days and dropped back down. Again, there's background rejection is what this is all about, and trying to convince the students the background instead of just rushing in and looking at events and saying, wow, there's a thing, and then going in and trying to figure it out. It's really about suppressing background events that come from noise of something flying through the field of view. The other thing we see on relatively short time scales are eclipsing binary stars. If you look at the next slide, yeah, this credit's on my book for stealing this picture out of there. To say, this is the classic shape of a contact binary, of a binary light curve. It doesn't have to be contact. We have a small object, this was in the lab book, you see it put on there, measuring the diameters of those from these. You see 2 objects, 1 object, 2 objects, 1 object. And by timing that, you can get diameters of stars and look for evidence of stuff, mass transfer, other things that would change the periods right there. So having 10 years of data, we have a lot of data to go in and look to see if there's been any eclipsing times. Pretty good clock, this mechanical system of these things moving around, except the stars aren't rigid. Stars are gushy, let's say. And so we have that to see if any timing changes occur. Either with flare stars or the eclipsing binary stars, one of the things that you have to do is you have to find them and understand whether they really are varying or not. And so we developed this technique that we call the Welch-Stetson variability index statistic test. And so we go through, and what we do, I won't talk about it too much, but one of the interesting things I learned, again, I come at this as an X-ray astronomer. For those of you who know about how these things work, the idea that my initial goal in trying to do optical astronomy was to measure the same star 5,000 times, make a histogram of the values, and look for single outliers. You look at that and think, yep, that's the way an X-ray astronomer would think about optical astronomy, all right. And so there's all of these sort of biases built into that, but I didn't know much about this, and so it was really interesting to me. I learned stuff as I go along. It was really interesting to me that if I plot, we take every frame and throughout a night, and we'll shoot 3,000 frames maybe on a given night, and to make the average brightnesses of the stars in each frame the same, what we do is we go in and we pick 4 frames throughout the night, and when we pick those 4 frames throughout the night, we look at, we average the brightnesses of all of the stars in there, and then we look at every other frame, and we take, okay, here's star number 3, compare how bright it was in this image to how bright it was in average in those other 4. We do all of that, and we find the median of all of those ratios, and so we have this normalization factor that we multiply each frame by, and that's what's plotted up here. And so you see, I mean, I knew this, that as the stars rise, they get brighter, and as the stars set, they get dimmer, and so the normalization factor gets to be smaller. You have to multiply by a smaller factor as the stars are getting higher in the sky. What I didn't realize is how almost every clear night you have this stuff going on the time scale of 10 minutes or 15 minutes or something like that, that you see these bubbles walking around, and you don't just get a nice smooth parabolic curve like that where there's stuff going on in the atmosphere, that transparency is changing, stuff's happening. So what we did here was we said, given that, if a star is looking variable to us because we have these unfiltered images and we try to normalize in this way, blue stars aren't affected the same way as red stars, and it hurts our normalization factor, what we could do is we could go in and say, at the same normalization factor, which is measuring the same effect of the atmosphere, a given star, if it's not variable, it should have basically the same signal. And so we can go in and we can make a graph of the signal of the star versus the normalization factor to say, instead of graphing versus time, which is what image number is down here, we could graph versus normalization factor and look at that, and you say, okay, here's what a variable star looks like then. A variable star, when you get back to the same normalization factor, it has 2 very distinct values of signal, and you have these nice, what we call these hooks in WSVI space. And we built this statistic to measure this in this space, and Rajesh and Todd Brown, whom we looked at earlier, helped us. Those were the 2 who really undertook using this WSVI statistic to try to measure stellar variability. And that's then our number 2 gray box right here. Is if I had a thing that I could say in addition to having students, these aren't in any order, by the way, these 1 through 7. They just as they popped into my brain and when going through there, just sort of. I would say they're random, but then I have to tell you a story. I promise not to tell you too much stories. I was on a search committee for the dean in our college a long time ago, 10 to 12 years ago. And so I was on a search committee, and you don't hire deans or presidents without hiring a consultant. You have a consultant who goes and tells you what it is you're looking for and why you're looking for it, and then develops the pool for you. And so the first meeting with the consultant, we're sitting there, and the consultants handed out this nice glossy brochure to us to look at, and it said, here are the characteristics that are important to you in your next dean. They had a list of them. And so the characteristics are listed alphabetically, and thus are random. Random order. Never mind. So anyway, these aren't exactly random order, but they are the order that they popped into my brain. And to say, here's a great way. One of the things is to help students develop a statistical understanding of data and a statistical way of viewing the world that's a little more sophisticated than we probably get to in the standard undergraduate physics curriculum. These students are all physics majors. We don't have an astronomy major. And so this is great. You see how this can do that when you see a statistic like that. Rajesh is an IT specialist for Pheasants Forever right now. Some eclipsing binaries. These are light curves of eclipsing binaries. So this is a fraction of a day here. So from 0.7 to 0.8 would be 2.4 hours, 10th of the day across there. So you see some of these eclipses that we have occurring in the orbital period of the system that we've measured. There's a beautiful partially eclipsing system where you never get the full flat-bottomed eclipse, but it just nips across there. That's one of the two stars that was known previously that was as a variable star. So we know that pretty much better now. There is one of our eclipsing binaries we work with quite a bit. There's a short period typically, right? Because as the period gets longer, the constraint that it be in our line of sight, the orbits, as the objects get further separated, the constraint that it lies right in our line of sight so that we see an eclipse gets to be more stringent. So we see a lot of these short period things. There was one night earlier this year where the 6 that we just saw, 5 of them were in eclipse on the same night. That almost never happens. And so we just normalized them all to 1. So we started 1 on the same scale, and you get a sense, sort of the biggest eclipse that we have there loses 30% of its light. That was 30-35% for these two when it's in eclipse. The one that was that one, purple triangle right there, is the one that was that nice sharp partially eclipsing system. Loses typically about 6% of its light when it's in eclipse. So we're back to the next key idea that we learned along the way. Nothing is ever clear, and in fact, not everything is clear. I say there. In fact, almost nothing is. Have you found something or have you not found something? And the students, when they read in the textbooks, again, they read the textbooks and they say, well, we discovered this in 1936, that this happened and this was this way. It seems like a light went on and all of a sudden the world knew that this is the way this worked. And we tell stories there too. We tell stories about people who first measured the wave nature of electrons but didn't publish because they were sure that they weren't right, and then had to share the Nobel Prize because somebody else got in there and published. But we also tell stories about people who were sure they were right, went and published, and they weren't right. And so you're walking this line all the time to try to say, well, did I just see what I thought I saw? And again, you use your statistics to go in to say, what's going on here? And so we'll sit around and we'll talk about, are we seeing this or are we not seeing this? Can we tell the world about this? Can we write a paper and tell the world about this? And the students are like, sure, we can write a paper and tell the world about this. Okay, it's my career that's probably most impacted if this is wrong, right? So what we do here is a little bit of timing these eclipses to see if maybe what we're looking for in this particular case is a couple of things, to see if this timing changes of where these eclipses occur over the 10 years that we've been looking, to see if maybe there's a cyclic walking around, or maybe if there's a trend in one direction. If there's a cyclic walking around, probably it comes, not necessarily, but probably it comes from the third star in the system. It's pulling the binary closer and further away, so that it's changing the timing of when you see the eclipses. And so we go and look on that, and we also, here what we're looking for is to see how circular the orbit is. We go in and put limits on the eccentricity of the orbit. We go in and say, is there a trend from one end to the other? If it's just walking, if the period's changing in one direction, most likely, not necessarily, that comes from mass transfer. And we go in and we put limits on how fast mass is being transferred from one of these things to another, to the other. And for this particular star, we're right. We could put an upper limit on here of what the mass transfer rate would have to be, and it's right at the edge of where it would be interesting for the next 10 years we'll tell the story with this system, probably instead of the first 10 years. But this is what we're working on, and this is what this is this idea that we really have to be careful to try to decide if we've measured something or not measured something in there. We look at the depths to see if the star is the same temperature or not. In this particular system that we're looking at, there's a lot more scatter in the eclipse depth. One of the systems is covered, one of the stars is covered than when the other star is covered. So that means that star that's being covered must, its brightness must be changing around, presumably from star spots, from the magnetic field of these fast rotating, fast orbiting things. Got a lot of star spots in there. So we look at that. Really, the students who worked the most on this project with eclipsing binaries, Nathan Ringstorff and Ujjwal Joshi. Ujjwal Joshi is a computer specialist at the University of Minnesota right now, and Nathan Ringstorff is in graduate school for choral directing at the University of Washington in Seattle. So we move on. Change to the stars that are changing on long time scales. Those are short time scale stars, the eclipsing binary. Most of the stars that we see in the field that are variable, that are clearly variable, are variable on time scales of weeks to years. Very long, they're pulsating stars. So we developed a different statistic, and I've done this work with Donald B. Brown, who's currently working with me, going to graduate this year. And to develop this thing, we started in-house just calling it an F-stat, and somehow that's become its official name, I don't know. Where we measure the variance of the star on long time scales over the whole data set and compare it to the variance of the star on consecutive nights, where we have consecutive nights of data, to see if it's varying more over these long time frames than it is over night to night. It just comes from noise in the system. And so with that, we found 55 stars that appear to genuinely be variable, that have passed the tests that we put on these things to say they have to have a value of this F-stat that's higher than some level. So this is kind of what they look like. So 3,000 days worth of data here for this star. You can see it varying from about 15.5 magnitude down to 19 magnitude. But we can probably see down to about 19, when we sum stack frames, we can probably see down to about magnitude 19.5. But anything below there starts to get really tricky. We fold the light curve, and you see pretty clean light curve, but not a great, there's a little bit of scatter in there. 154.29 days was what we folded that on. So then we go in and we look for properties of these stars to see if that help us classify these stars and think about these stars. Here's one of the stars. Right there. There it is in April of one of the years. There it is in August of that year. So you can see the actual brightening of the star across it. That's one of them that has the larger amplitude for us. We look at the populations. We do a date compensated discrete Fourier transform to try to measure the period, and you can see the leading term in the power spectrum, as we'd say out in here. And see these stars that are up in here that have a very high leading term in the power spectrum, they look clean. That's the star we just looked at in the image before. 13.5 magnitude down to about 16th magnitude. So very nice clean light curve. You get stars that are some pattern right there, and then you get stars where we can't with a single period. That was 321 days. That's 193 days. That's 118 days. With a single 118-day period, we can't fold that light curve and get anything clean out of that. And that's because it's pulsating in two different modes simultaneously. It has two or three. That star actually has three different periods. Oscillation. We go in and try to decide how many stars are actually variable in there, because our detection efficiency drops off rapidly with amplitude. So this is what we see, the distribution of amplitudes of pulsation around 3/10 to 4/10 of a magnitude of amplitude. There's this big peak, and then we have these high amplitude stars that are out in here. These are the stars, high amplitude stars are the stars that are pulsating for the most part, not entirely, in a single mode. And then we have, most of the stars are double or triple mode oscillators that we see down in here. But we knew that this probably isn't real, this edge. That's just our detection efficiency. We can't detect the lower amplitude stars with much efficiency. So we go in and try to estimate, given our statistic that we're using as a function of amplitude, we do a fit to that and try to estimate what our efficiency is at detecting these things and say the real population looks something like this. The error bar is large enough down in there that we still can't really say whether it turns over or not, that distribution. This is everything I just told you. Now you can read it, so you know it's true. So we ended up estimating that as a percentage of the stars in the field that had amplitude of 0.22 magnitudes or greater, had a period longer than 10 days, our F test doesn't work for, it's inefficient below that. We had about 4% of the stars, 3.5% of the stars were variable with these parameters. If we took out none of them are in the M23 cluster, okay, that foreground cluster. So if you take out the foreground cluster stars, that number doubles basically to 7%. And if you've been paying attention, and I know you have, at least nobody's called the police, no, so far as I know, nobody's called the police on it yet. But that doesn't quite jive because I said about a quarter of the stars were in the field of view, were in the cluster, and then you see this doubling in this number when you take out the cluster stars. And that has to do with stars that weren't in enough nights. They were in a lot of nights, but not enough nights to pass the test that we said we had enough data on to do this. So the populations of pulsating stars that we looked at, 3 students have really worked on this, and so we're going in, there's our high amplitude stars again, look like a distinct population, single mode stars from these other stars. We look at the colors of these stars and how the amplitude depends on the colors. We've got a tight cluster of these stars that are down in here, pretty red. All of these stars are pretty red, well almost all. We'll talk about these 2 stars. And then you've got these high amplitude stars that are scattered along there. Amplitude versus period. We do all kinds of assessing this stuff. And a lot of this work done by Carrie Frank. She's at Purdue right now in an astronomy graduate program. She'll be very close to finishing her PhD. Andrea Schiefelbein works with Epic Software Company in Madison. Computer, it's a hospital building software company. They hired a lot of our graduates. Alex, last I heard, he graduated last year, and last I heard he was still discerning his future. So, not sure where he is right now. We have here 2 of the yellow stars in the field that weren't as red as the other stars. One sure looks like it's a Cepheid variable. Very interesting stuff to me. Again, I don't know much about these stars. Very interesting to me that the amplitude has been growing consistently over the 10 years that we've been observing, and the mean magnitude of the stars has been getting fainter on average. This data up in here is from early years, and the different symbols. That was a very recent year. It doesn't have this year on it. This year is actually down here, even bigger amplitude and fainter on average. This is an RV tau star, pretty sure. This is the other star that was a known variable star in the field of view. It was in the GCVS, the catalog of variable stars. It was in there as a semi-regular star, but given its color and the fact that it seems to show an alternating deep minimum followed by a shallow minimum, sure suggests to us that that's an RV tau star, a much rarer kind of star. You see right there, a different place in evolution. So we get to our 4th gray box, and it says, the other thing we're trying to learn from this, and it's related to one of the other things that we said, everything we know about the universe comes from this kind of work. If you look in the textbook, you say, well, Ohm's law is V equals IR, and it just seems like, well, there's Ohm's law, and the students are happy. Somebody worked hard, Ohm, and maybe other people, worked pretty hard to make that a reality so that it could be in the textbook for us to learn like that, and it's not just there. It doesn't just appear out of nowhere. You've got to work and work and work and work at this stuff to make this stuff happen. So the kind of work that we're doing here, we talk about this and say, everything we know about the physical universe comes from this kind of work, and people have been struggling with this for hundreds of years to put these pieces together, and they weren't sure they had it right when they put it together. Some more interesting stars. These we call plateau stars. These are stars that consistently stall as they're getting brighter. You see in the folded light curve there, these stall regions for these stars. There's one that's not folded, but you see a stall right there as the star is getting brighter. What we call sudden amplitude shift stars. Walking along, walking along, walking along. Interesting, looking variable, but then bam. And it blows up there, and then sometimes you see the one up here blew up and then went back. What we think is going on there, we're working on this, Donald and I are working on this right now. What we think is going on there, two modes of oscillation that are interfering with each other. One of those modes goes away, and we don't know why. And then you've got a single mode left, and you suddenly get that mode where you don't have this sort of chaotic behavior, where you have that mode of oscillation that's dominant. And then for this star, it looks like we're right back to having 2 or 3 modes excited again. These are the modes you've presumably seen standing waves on the screen before. And so we talk about this to say stars are more complicated because of, well, they're three-dimensional, there's density variations throughout the thing, and there's ionization that goes on inside the star, ionization zones and non-ionization zones. Much more complicated, but this is the kind of thing where you might have what we're trying to figure out right now, do you have an n equals 1 and an n equals 3 radial pulsation going on? Is there non-radial pulsation going on where different parts of the star are doing different things? And we do this by fitting this big compensated discrete Fourier transform that I talked about earlier. So we get to number 5 in our list of specific tools and techniques that can be useful in a variety of ways. The kinds of Fourier analysis that we're doing, I suspect electrical engineers might find useful on an ongoing basis. And the students, the statistical tests that we're applying, hopefully the students, what I do, I'll tell you this. I'll tell you this because if you go to the Wilkerson College website and they have these profiles of people that pop up, and 1 out of every 100 times mine pops up, so you might read it if you go there to just look for it. And what I do is every Halloween, I count the number of trick-or-treaters that come to the door in 15-minute intervals. And then I make a histogram, and I fit curves, a Gaussian curve to that histogram, and I can find out scatter year to year what the variation in the number of trick-or-treaters is, and I can tell you that 6 to 6:30 is the peak time every year, and how many trick-or-treaters are likely to come after that. So then it's a useful fact to know if you need to run out and buy more candy at 7 o'clock because there's peaks here. And I also, what I've learned this year is I can tell you how much that shifts later if trick-or-treating is on a Friday or a Saturday night or a Sunday relative to the other days of the week. So you see how the tools that we're practicing here are unbelievably useful. You got to do that kind of stuff. So this is Donald I've been talking about that I'm working with right now. This is a graph he made called a Peterson diagram. I didn't even know such a thing existed. I went on vacation, I went fishing for a week here this summer, and I came back and Donald had discovered this Peterson diagram in a paper by Kiss et al. And he started explaining it to me, how this worked and what had gone on, and he'd taken our data and plotted the ratio for the multi-periodic semi-variable stars, plotted the ratio of the 2 dominant periods divided by the ratio of the 2 dominant periods against the ratio of one of the periods like this, and you see that they cluster in bands. So this, almost 2 to 1, 1.8 to 1 is the period ratio there, 4 to 1, 7 to 1, 10 to 1 period ratio. Presumably these are stars that are in different excitation modes, like a third and a second, a fourth and a first, and things like that. And presumably these stars evolve from one band to another band and what's going on here. But we don't have a good handle on it. We're working on it right now. But I went away on vacation and I thought, well, okay, I should go away on vacation more often because we learned a lot in the week that I was gone. And this is the thing, another thing that's really key to these students that I work with, and that's development of project ownership. That this becomes, the goal is for this to become their project. They don't have to be talking to me all of the time to do things, and they're out there thinking about these things and working on these things and doing these things. And this is a great example of that. Donald has dived right in there. Donald can do that because this was the 3rd summer that he's worked with me, right? So this doesn't happen overnight. This is the kind of thing that's a nice development that you see going on. He can be thinking about this and doing this kind of stuff. And some students never get there. some students I'll work with for a while, and we'll make progress on this particular goal, number 6 here. But the students just don't quite turn the corner at being able to really on the project. They're really not wanting to come to see me about every little thing that they're doing. About saying, okay, what should they do next? And what should they do? That's usually the trajectory, right? That first summer, that first week, I'm sitting in my office, and every 10 minutes there's somebody at my door saying, okay, what should I do next? Okay, what should I do next? And the goal is, by the end of working on these projects, I get to go fishing every day and come back and say, look at that, I'm famous because I went fishing and somebody did work for me. So, Donald, by the way, he graduates this year. He's going to go to graduate school in astronomy. And we're trying to find the right fit for him now. Another thing that I tell people all the time, doing astronomy or physics is a lot like writing poetry. Every detail matters, and you spend all of your time worrying about those details. You sometimes forget that there's a big picture out there, and that's what you're looking for. Growing up as an X-ray astronomer, those details were in the lab where I was breathing solder flux day in and day out, and looking at signal and so on, and trying. And if you get that right, then you have a chance to make a step closer to, I don't know if I want to claim that it's truth, but beauty, certainly, that you have a chance to do something that's interesting and special. And I put on the page the oddities that we see here that we have to deal with, that we have to take out. There's an asteroid that's passing right next to that star. That's an asteroid that went right through that star. Sure looked like the star got brighter for a few hours. So we see these sorts of things that we have to deal with. That's the shutter of an Apogee AP6E camera that sticks open on a regular basis. And you recognize that you got problems with that. There's a satellite that went through the field of view. There's a satellite, a fake satellite that's tracking through this one that I don't think you can see. What you see here, I think, is from the angle and the timing of that, I think that's actually a Perseid meteor that went through our field of view, given the direction that I could track it back through. Most of the satellites go through in one particular direction. This is a very different direction, and if I track it back to where it came from, it looks like it's coming from the radiant of the Perseid meteor shower. This is what happens when you try to take images, because you just don't know when to give up. You try to take images on a night when the moon is 80% full and 12 degrees away from the cluster. And you look at that and you think, well, maybe it's not going to work this night. I should probably go home and sleep. If you know one of your eclipsing binary stars is going to be an eclipse, then it's really hard to make the decision not to go in and get that information. So, where are we? We've observed 59 new variable stars and starting to learn something, a little piece at a time. We learned something about how they behave. 24 students have grown in all kinds of varieties of ways. They've gone on out into the world and done all kinds of different things, and are about to go out into the world and do all kinds of different things. And we've had fun working on these things together. There's a quote from Edward Purcell, who won the Nobel Prize for nuclear magnetic resonance, and this is from his Nobel Prize like in 1952. I remember in the winter of our first experiments, just 7 years ago, looking on snow with new eyes. There the snow lay around my doorstep, great heaps of protons quietly processing in the Earth's magnetic field. It's just beautiful and neat. To see the world for a moment as something rich and strange is the private reward of many a discovery. And I'm not sure that my students and I ever get to the point where we see the world as genuinely rich and strange from the stuff that we've done. But we do have one last gray box to put up there. And we talk about this a fair amount, to say, at the end of this journey, or somewhere along this journey when we're doing this stuff, there's a moment when we know something about the universe that nobody else in the world knows. That we see something for the first time that it may not be a big thing. It may be that you don't take data when you have the full moon 12 degrees from your cluster. People probably know that. So you see something that we've learned about these multi-mode pulsators are just a star that was variable that nobody in the world knew was variable before. And in the end, we hope we get to the point where we recognize that as its own little one. So, thank you.
Questions for our speakers? How do you get students to work during the summers? Do you
We
them?
pay them.
Okay. Where do you get your money?
Generous donors. So we get the money from two places. One, the dean's office does fund about a dozen student faculty collaborative research projects across the campus in the summer. And typically physics department will have one of those. And then we had a donor for a number of years who donated a small amount of money, but did so on a regular basis. And we decided at one point to say, ask if we could put that into an endowment, and instead of just spending it out each year. And that endowment has gotten to the point where it funds 2 students per year, and we typically have enough grant money around that funds another 2 students. So for all of us in the department, we could typically fund 5, 6, maybe 7 students per summer to do this. We don't pay them as much as they get for going to REU program, research experience in undergraduate institutions. So that's just tell them we can't.
How much do you pay?
How much do we pay? $3,300 for 8 weeks. And housing, we pay for housing, we have to pay for it. Yeah.
I didn't hear if you mentioned what filter you're using. Were you doing this unfiltered?
Unfiltered most of the time, and then about once a year we shoot just standard DVRI to make sure we don't.
Oh, okay, so that's where the color stays on.
We shoot once a year, we go in to see if the colors of the stars have changed and do color correction factors to get the magnitudes
Sure.
right to convert from these unfiltered images.
Let's thank our speakers.